So here are some common activation functions for nonlinearities. First is the sigmoid function. This is what's being used in logistic regression. You have a range of 0 to 1. Sequence got messed up again. Let's just output everything. Okay. So what are some of the issues with sigmoid function? So it can kill the gradients. The exponent is very expensive to compute, and then the outputs are not zero-centered. So what's the issue with non-zero-centered data? We'll show it in a bit. So why does it kill the gradients? If your values are very big, it will be somewhere near this area or here. And that means your value is like almost 0. And if you have a value like that, then it will kill the gradients. You end up with a vanishing gradient problem in deep learning. So it can happen from time to time if you're not careful with the preprocessing. There's so many things that you have to take note of when you do deep learning. There's just so many hyperparameters. Let's just skip this part, but that's basically it. That is the issue. So why do we want zero-centered activations and zero mean data? And follow this later, but what will be the gradients? It will either be all positive or all negative if the input that you have is always positive. So what are the implications of that? Then the directions that you can represent using sigmoid could only be in the first quadrant or third quadrant. What does that mean? So for example, this is the minimum error that you have. It will take, this is supposed to be legit, but anyway, this is the optimal update direction. So this is what's going to happen given that input. So your updates would be forced to zigzag if all your inputs are all positive. That is one of the issues with sigmoid functions, because you end up with values ranging from 0 to 1. Now your data is not centered, not zero-centered, and this is what's going to happen eventually. So it needs more steps for you to get to the optimal value. Still following? Note that sigmoid can still work. You can use it for many problems, but these things could happen if you use sigmoid in neural networks. Although when you do neural networks, this is like one of the default things that you will see use sigmoid function. But recently, it's really in other activation functions. But yeah, just so you know, you can use other activation functions. Please use them. So this is a sigmoid node. If you're going to implement that, it is simple. And then the derivative of that is also very simple. Okay, what else? You have the hyperbolic tangent function, or think of this as the scaled version of sigmoid function. And it looks like the sigmoid function. It's just a zero-centered now. And then it ranges from -1 to 1. So because of that, you don't have the non-zero centered issue that you have in sigmoid function. But it also has the same problem, wherein you could kill the gradients if you have very big values. It's very small or very big. Because if it's very small, then you get almost -1. Sorry. Scrap that. What I mean was if it's near -1 or 1, the gradients will die if it's here. Should be near here. Sorry, let me think about that part. I think there's something wrong with the statement. Just remember, saturated near -1 or 1 near scale. Yeah, that makes sense. Sorry about that. That is correct. I was thinking of another thing. Yep, it can get saturated if it's near -1 or 1. So you'll have you almost have no change if it happens. Still the same issue. And then once again, the E is very expensive to compute. It is this. If you're going to implement the hyperbolic tangent function. Okay, now we have the rectified linear unit function. And this is one of the more popular ones. By default, you should use this. So it's just max 0x. Very simple. It does not saturate if it is positive, right? Because there's no limit here. Unlike NH and then sigmoid, right? It'll get saturated. Okay, the outputs are not zero saturated. So that's one problem that you have. We're still die to greater than 0 when x is less than 0. So basically the neuron is dead. If it happens, then yeah, you don't use that neuron anymore. But it's computationally efficient. There's no EXP. And then it converges faster in general, about 6 times. What else? There's also the leaky ReLU function. It does not saturate because you don't see it's not sigmoid or hyperbolic tangent. The outputs are not zero centered. That's one problem with this, but it will not die because of this small adjustment that we have here. If it is negative, then you'll just have a very low gradient. That's it, low output, but it won't die, unlike ReLU, where it just becomes 0. That's it. And similar to that, it is more computationally efficient. Similar to ReLU. Rectifier. What else? You have exponential linear unit function. What's this? It does not saturate. It's this one in the blue graph here. It does not saturate, and the outputs are more zero-centered. And it will not die. But there's the XP once again, so it's not really fast compared to ReLU. So in practice, use ReLU as a default activation function. It works well in most problems, but you have to be careful with your learning rates. You have to configure this one. You can try ReLU or ReLU. You can also try Tanh, but don't expect much in general, and don't use Sigmoid. It can still work, but you have to pay more attention to the gradients, because they might die. You might get vanishing gradient issues. Any questions?